So welcome to the course on nanotechnology. I'm Dr. Anita from Department of Physics. We have been discussing about what matter is, what is a nanomaterial, how a nanomaterial is made up of semiconductors, metals, and where all they find applications. Now let's move on from this journey of nanomaterials into the next world that we call as the meta world. Here, metamaterials are completely artificial materials. You take the same nanomaterial and arrange it in a particular pattern either. This gives rise to further new properties for the same material. So such materials which are artificially designed to suit our applications are called as the metamaterials. So metamaterials, we can call them as synthetic structures whose electromagnetic properties are beyond what we observe in conventional materials. And why we want to go for these metal materials are, these metamaterials also serve as an effective continuous medium for electromagnetic radiation. This metamaterial can control the way electromagnetic radiation is propagating. You can make the electromagnetic radiation move faster, you can make them move slower, you can make the electromagnetic radiation interact for a longer duration inside the material. So that way, metamaterials have the ability to control electromagnetic radiation beyond what we have imagined. So this gives rise to many applications which were regarded as impossible. The important example that I would like to give you is about photonic crystals. These photonic crystals are structures where the nanomaterials or subatomic particles are arranged in a periodic fashion. So it is the periodicity and the size of the particles which decides what color or what energy can propagate through it. And its path of propagation is also decided by the periodic arrangement in the crystal. These photonic crystals are man-made, but the idea for these photonic crystals have been derived from nature. For example, a peacock feather, you can see multiple colors in the peacock feather, whose color changes depending on how the sunlight falls on it or the way the peacock is moving. This is because the feathers, the small structures in the feathers of the peacocks are arranged in different patterns. So depending on the pattern of their arrangement of the nanofiber-like structures in the feather, the color it reflects also changes. The same type of behavior is shown by a butterfly. Similarly, the precious stone, which we know as opal, it's a naturally formed precious stone. The multiple colors we see is also because how the silicon dioxide particles inside the opal is arranged. So the arrangement in the opal takes place by self-assembly, that is, it happens naturally, whose arrangement is further decided by what is the temperature in the region or how long it is being exposed to that particular weather condition. All this decides how the silicon dioxide is arranged, and that gives rise to the beautiful colors that we observe in the opal crystal. Same way, certain moths are there whose white color is regarded as the whitest ever, which means it is scattering all the electromagnetic radiation. Similarly, the shiny beetle, the golden color of the beetle, the metallic structure of these beetle, it's also because of how the particles in the shell of these beetles are arranged. So if you look at photonic crystal, which can classify them into three types, they are either one-dimensional, two-dimensional or three-dimensional. In one-dimensional periodic structures, you can see there is periodicity along a single direction. And in three-dimensional, in all the three directions, you can observe the periodicity. And this type of a structure, depending on the periodicity and also the size of the particles, it will reflect different colors, which is called as the photonic band gap. So rest of all the colors it will reflect, and one type of a color, depending on the periodicity, will get reflected. So this gives rise to an unusual control over what color of light you want to transmit and what color you want to be reflected. Thus, we can easily manipulate the flow of light through this material. This has given rise to many applications, especially in fiber optic cables. In fiber optic cables, we know that, of course, fiber optic cable is following the principle of total internal reflection. It has lots of advantage when you compare it with the coaxial cable for communication. But there is a single major loss in fiber optic cables which happens whenever the cable is bending. This can be prevented if we are going to make a fiber optic cable made up of photonic crystal, because here we decide exactly what wavelength has to be transmitted, and whether it is straight or if it is bent, only that particular color will be reflected and it will never be transmitted. And so when there is zero transmittance, the loss is also zero when you are making a fiber optic cable using a photonic crystal structure. So this photonic crystal technology has been adapted for various applications. It's also giving rise to one more significant phenomenon, which is we call it as the negative refraction, or making of super prisms, making of super lenses. So negative refraction, we know that whenever light is traveling from a dense medium into the rarer medium, it gets deflected away from the normal. So this is the way the normal reflection is. But if you're going to make a medium out of a metamaterial, you can change the way the light is getting refracted. So now when light is traveling from a dense to rare medium, instead of moving away from the normal, it will be refracted towards the normal. So this way, again, we can control how the light is propagating through different mediums. So this was first observed and reported by Viktor G. Veselko, who is a Russian physicist. He found out negative values for both permittivity. Using this type of a material, we can have both right-handed and left-handed materials. So this helps us in making super lens, where the focusing ability of the lens is much higher compared to ordinary lenses. We can also make super prism where the dispersion of the light is much higher, and this can also used for various displays and lighting effect. Making a filament out of photonic crystal not only improve the illumination of the lamp, but also reduce the heating effect by not allowing IR emission to escape out of it. Also, one of the most wonderful thing that a photonic crystal can do is we can reduce the speed of light to a very small value, which is so small that we can say you can almost walk with the light. Light travels very fast, which is around 3 into 10 to the power 8 meter per second. This is through vacuum. But as it goes through air or then through water, its speed gets gradually reduced. But still, the reduction in speed is not that small, and we usually don't observe the change. But when the medium is made up of photonic crystal, it becomes so slow that it moves along with a bullock cart, or you can also walk along with the light. What happens here is most of the particles in the photonic crystal start exposing itself to the light energy, and there is a enhanced amount of interaction between the light particles and the nanoparticles which makes up the photonic crystals. So this increased interaction delays the propagation of light, giving rise to slow light. This has two advantages. One is you can gradually control how the light is propagating through the material. Also, because of this increased or enhanced exposure between the light and the material, it gives rise to increased properties. So applications like sensors, LEDs, photovoltaic devices, lasers, they show multifold increase in the properties just because the light is traveling much slower through the material. So this type of a light, we also call it as the slow light. So they have lots of applications, for example, in lasers, in optical switches, modulators, memory devices, in integrated circuits. So here you can, of course, reduce the energy of the light being passed, and the size of the particles can also be reduced, but still giving a much higher efficiency compared to what you observe in the conventional devices. Thank you.